So this is probably just a little bit of a gear shift. I'm going to talk about our experience with integrating and exploring DPDK in a product. So integrating it into an application that already exists and the challenges that we encountered along the way. I'm Roger Melton, by the way, from Cisco Systems, and I know I'm looking at you over my glasses. When my father did that, I thought he was angry. I'm not angry with you guys. I just can't see unless I do that, and I can't see my slides unless I have my glasses on. But I work in the Enterprise Networking Group at Cisco in the data plane technology team. And I'm just going to give you a little background on the products we work on, not anything deep, just a quick overview, no real details because I'm not allowed to. And then just give you an idea of what we did with our experimentations and observations we made and where we think we're going. So our data plane, what I work on is the iOS XE data plane. It's a large shared code base with a common architecture. It runs across many different platforms on Cisco ASICs with thousands of cores. It runs on commercial multi-core, so on ARM, on MIPS, on x86, or on a commercial multi-core in various hypervisor environments. So it's quite the number of different platforms that we have to support with this common code and common architecture. The performance range for this code is anywhere from 50 megabits to 200 megabits and beyond, or gigabits and beyond. We build with legacy tool chains to modern tool chains. We use open source GCC, custom GCC, for some of our ASICs as well. We use ICC and Clang. So lots of tools that we have to use. We work all the way back to the 2.6 3x kernel. So, if you're depending on things in DPDK and modern kernels, sometimes we don't have them in the older kernels, so we have to deal with that. We have to support both 32-bit and 64-bit applications. And as I said earlier, it's anywhere from a single core, multi-threaded, to thousands of cores with this same code. It's deep in a layered system, so we're not sitting on a Unix or Linux command line, typing in the RTEL, ARGs. That's all got to be integrated into the system. So I think probably our reasons for experimenting with DPDK were similar to everybody's. We, first and foremost, it was performance. So, how do you get that? For us, there's many different ways, but reduced system calls. So, POMO drivers help with that quite a bit. Simplified I/O batching, so, bursts and bulk. No ISR. Core utilization is very helpful. It's easier to debug a POMO driver when it's in user space than when it's in the kernel. So if you're writing your own drivers or hacking them, it does help there. The fact that your memory is now isolated from the kernel is helpful as well. So your application can crash without taking down the entire system. So we approached this in two phases. We had first just an experiment to integrate it into our data plane. So it was quite a task to do full integration, where we integrate with our control plane and our data plane and the entire system in itself. So we started off with just integrating into the data plane. And our primary interest was trying to get to integrate it for I/O. I mean, getting packets in and out as fast as we could was what our goal was. And of course, if you're going to bring I/O in with DPDK, you got to bring some other things too. So you have to have the memory and buffer management. You have to have some thread management where, if those threads are using DPDK APIs, then it's some of them are required to be DPDK RTEL cores. So it's safer to make those threads DPDK threads. we decided in that phase to just adopt the sort of standard build environment and runtime environment, so no cross-compilation we were using. I think when we started it was Fedora 16 at that time. So we built DPDK in the normal way that everybody's used to. We built our data path. Actually, the harder thing for us was taking our data path and building it on a Fedora system than actually using DPDK at that time. And then we just linked to the dynamic libraries as you're used to. Then after that, once we saw that this looked like it was going to be a valuable pursuit, we just decided to do full integration into our build environment. We have a custom-grown build environment, so we can't use DPDK build environment. We had to replicate that to a degree within our environment. And then integrating it into our runtime environment. So this system boots up, it's running Linux, we have init scripts that go out and initialize interfaces. All these things we had to do in order to use DPDK in our data path. And then our control plane had to be modified in order to manage this as well. It knew quite a bit about the underlying physical devices, I guess, and to do physical device management.
Yeah, just to go back to that, we found that we needed some infrastructure within DPDK to try and abstract out this port concept. So we've actually got a namespace mapper where you go off and you can ask it, hey, given the port, tell me the equivalent Linux name. So you've got to do that mapping, and when you start when you start looking at multiple architectures, that's got to come in. So we'll let Stephen submit his code because it's probably less buggy than ours.
Actually, a lot of internally, we made the conscious decision to use the same naming algorithms as the guys do for systemd, so that the distro name is related to the internal name. So we could we could work with those guys and expose that algorithm. It's fairly straightforward.
Yeah, but when you start looking at things, you find out you really need it.
Yeah, you do need it, and it would be actually useful for, I think, for people to be able to say, I've got this PCI device, what would it be named in the NetDev systemd world?
Right, and as I mentioned, we're working with a pretty old distribution, if you will, so we're UDEV, right?
So systemd subsumed UDEV,
yep.
They subsumed everything else.
Right.
And they developed a policy set of rules, and as good as any other,
Yeah, it's different, right? It's different. My point was that, if you're using UDEV versus systemd, as long as you can adopt it and you can use it independent of which device management you're using, that's important. So the next slides are just about observations we made as we went through this process. And we started actually, when we started playing around with it, I think, it was DPDK 1.3 something when we first just picked it up and played with it. By the time we got really involved with it, we were at 1.6. So one of the first things we ran into, and I'm sure other people have hit it too, was if you have a multi-threaded application that needs to scale down to a single core, it was not possible, right? DPDK said 1 L core per physical core, so that was a challenge for us, and I'm sure as others did. I talked to Larry sitting over here on the front row quite a bit about that. We talked to them about the issue, and fortunately in DPDK 2.0 that problem has been solved for us. So now, we can start multiple threads on multiple L cores on a single core. There are a number of different ways to do it. So that's really helped us out a lot. Another issue we had, I think Stephen, you'd mentioned it yesterday, was and it got mentioned again today. In a VM environment, new map lies. So, we had some issues with that where, we're bringing up the system and, you have things like physical device ID being used, and in the VM environment that may or may not be true, right? Depending on how you've got that VM configured. One of the other, probably one of the more difficult tasks we had was that UIO eliminated those traditional, Unix, Linux ways of getting to managing devices. So, ifconfig, ethtool, all those things were gone. And our control plane uses them to do physical device configuration. So it was an easy way for us to do it. Before DPDK, we could just go, use those APIs, use the ioctls, and everything worked fine. But with UIO, the device is gone. We had no access to those APIs. And we looked at, yeah. I'm having a hard time hearing you. So do we have the mic? Oh, Andy's got it.
We are trying with some of the devices, and we start with the Mellanox to have the PMDs, which is a kind of bifurcated logics. And did you try to use it for the ETH2 and others? And if yes, did it match your needs?
We did not try the Mellanox. Now we talked about to Intel about the bifurcated drivers coming for the and the issue we have there is we have to support many different types of NICs. So if every NIC didn't provide a bifurcated solution, then we have to have multiple solutions. So we were looking for a single.
And someone I'm trying to understand, it could be bifurcated driver solution because there are some security issues with the bifurcated driver. And try to understand, let's say if the model works for you as a user, because as X16 we have some similar needs. So if it works for you, just as I was saying yesterday, maybe it's become very important that we push a kind of rewrite or update of all the PMD one by one. Of course, the world will not change in a day.
Right. So this where we ended up going was this ethtool API that we worked with Intel on, and today those APIs have been pushed into IXGB, IGB, VirtIO. Right? Is that right, Larry? Okay, that's not so IGB, but we will be working to push those into VirtIO, VMX Net3, so that the other pole mode drivers can take advantage of these.
That's the next workaround, but it means we keep stacking on the problem instead of, let's say, removing the problem. So we keep increasing the complexity of the open source maintenance of the DPDK.
Okay.
I'm pretty sure Steve has some comments about the education.
I hate to have anything we have to change 100 drivers if we'll get to at some point. That's going to be a real problem.
Right. Well, if you integrate a new driver and adapt it at that time or adopt it at that time.
The barrier to entry is that much higher for the next piece of hardware that comes along.
Yeah, that's true. That's true. But still, I mean, it's I think we'll be faced with problems like that, and you have to take them on a case-by-case basis. And that doesn't mean this is the best solution. It's what we came up with and what worked for us. And if there's a better way to do it, we'd certainly consider it as well. So like I said, we looked at K&I. K&I didn't work for us because it only supported IGB and IXGBE. K&I also had some other limitations. It didn't support 32-bit compatibility ioctls. So if you need a 32-bit application in a 64-bit kernel, it didn't work. So we limped along for a while by just hacking K&I to allow us to do IGB, IXGBE, but that wasn't a long-term solution. And the bifurcated driver, while interesting, as I said, it didn't support all the NICs, and it was a little heavyweight for what we wanted to do as well, as was K&I, because all we're trying to do was really get to the device. We had no interest in sending packets back and forth to the kernel network stack, so that all that extra functionality wasn't really interesting to us. In fact, it was baggage that we had to carry if we would pursue that. So we decided to pursue the ethtool approach. And I'm sure, we could talk about that more in one of the lightning or the open mic things if people are interested in talking about that more later.
Yeah, and Larry Wang here has got a paper where we discuss different ways of doing it. As Roger said, there's trade-offs all over the place.
Yeah.
Let's get the collective IQ points in. There's some code sitting there ready to go into 2.2. So people want to look at it. You know, I'm open for other suggestions. As Roger said, we needed this problem, we scratched the itch. We've got something that hasn't seemed to fail. It does have the issues that Stephen pointed out, where you end up replicating lots of other stuff. There are other things suggested in the paper that are more hybrid type things, but you know, they need it. Again, we need to think about them a bit more.
Mm-hmm.
Where's the paper?
Hasn't been published yet, so it's on Larry's laptop.
You have dev at dpdk.org, and we have it in 5 minutes.
What's that?
You can send it on dev at dpdk.org, and we have it in 5 minutes.
Okay, there you go.
Yeah, no, last time we posted to dpdk.org, we caused a bit of a stir. I think we have the most number of check-ins. I think we got to 17, and then just like all good managers, we renamed it so it went down a bit. But you know, we want to. Well, we've got up our profile now. At that point, we were trying to keep a lower profile because of, I guess the Ericsson guys said it best, internal politics.
Yeah, there's a lot of internal politics. Also, we were drinking from the DPDK fire hose, right? We're trying to learn it. We're trying to adopt it in our environment. It's you know, we weren't comfortable with actually coming out and contributing until we had our feet on the ground. So we're, you know, hopefully we're there now.
I will not comment on that. Just small is beautiful at 6 minutes. So just one comment about the polling. Did you try, and because I've been trying it and we're failing, to use a kind of dynamic RSS, so for instance, all the cores are there. Most of the cores of DPDKs could be sleeping. And the RSS, let's say everything is tier to one course, so at least one course keep being busy, or one L course in case of DPDKs, and then we add some RSS queues, we remove some RSS queues depending on, let's say, the workload, and when we attach RSS queue to the L cores, then these L cores start to run. So it's a bit of kind of compromise, because you need to estimate the workloads, but sometimes we can...
Yeah, at the moment what we do is we speculatively sleep. So if as long as our data path is busy, everything's fine, right? I assume we're talking about that 100% PND RX core occupation. So at the moment, if we end up in a situation where all of our ports go idle, we have some hysteresis. We'll sit there and poll for a bit, and then after a while, we do a short sleep. So, you know, if there are other ideas about better ways of, you know, doing a quick sleep and wake up, that would be helpful. We're not very efficient at that right now, but that's what we do.
What about scaling frequency of the board acting about that?
Well, we're in an environment where we don't have control of it, so.
Yeah, we played with the same game, and I decided not to do the frequency scaling because you're running on a VM where you have no access. So, you know, the worst case is on a VM, and then you're not going to have any access to that. And if you're on bare metal, it probably doesn't matter as much.
That's right.
I played around with a whole lot of different hysteresis algorithms, and you know, some were awful, and most of the obvious ones were fine. The interrupt stuff helps a lot, but it's once again, you need to support on every device before it gets interesting.
Yeah, that's until it's there everywhere, we have to have multiple solutions,
right.
And that makes it hard. Some of the other stuff with the interrupt, I have a bullet on it later, but we may as well talk about it, was, you know, we needed the ability to have individual interrupts from every port, and then we need to be able to, you know, let's say a link comes up or goes down, or I shut a link so it's no longer, but I'm waiting on that guy, right? He's off waiting on internet. I want to be able to remove it from the event loop, right? So there's some things we need to be able to do to solve those sorts of problems as well. So.
Yeah, but just like Stephen was saying yesterday, I mean, Cisco, we've been using the NAPI-like thing since 1993. It's an obvious thing. Somebody took away our toys. We need them back. So,
yeah, and with that, you know, you can still have a little heuristics, but they're way less sensitive. You know, you may want to say, "I'm busy. I was busy. I'll keep polling," but you know, the wake up time is so much. Oh, the other thing,
that's the problem. Right?
The other thing that was helpful on this, and I'll mention is it turns out if you're mark those threads as real-time threads, they wake up much faster. The normal kernel scheduler, if you say, I want to sleep for 100 microseconds, 100 microseconds, maybe 500 microseconds,
That's right.
It doesn't care. But if you say you're a real-time thread, it's going to say, okay, the clock's 100 microseconds, here you go.
Yep. Yeah, we've played with that too.
It's really, I mean, that's surprisingly accurate.
But if you're in a VM, the other problem is, you've now got a scheduling opportunity for
Right, yeah.
to go off and let the host do something else for a while. So the lack of determinism there is a problem, right?
And the other weird thing about that whole thing is how long you sleep ends up getting totally interacted with P states and C states on the processor, and it's really
Right. So and I don't think I actually mentioned it, but our focus right now is running in a virtual environment. So we do testing in a bare metal environment, but anybody that buys this product, they're running it in some sort of VM, KVM, ESXi, Zen, whatever.
Yeah, and this is where the hardware vendors can help out a bit, because when you're in a VM, things like memory access, disk access, the VM knows when it wants to do that access. With a network packet, it doesn't come in. So anything the hardware vendors, Venki was talking about branch prediction. If you can do branch prediction when a packet's coming in, we'll all be pretty happy. And then M-Wait in Ring 3 would be nice as well.
Yes. So I think another recent observation we've made was related to the packet mbuff cache. It really is. We haven't looked into it deeply, but it appears to be optimized for RX and TX on the same core. So we had done some experiments where we were, moving RX and TX around. We've got multiple ports. So TX might, RX may come in on one port, go out on another, and the TX is actually, we're not running to completion. We actually have sort of a pipeline where TX may come out on another core. And, what we noticed is if we end up in a situation where there's an imbalance between RX and TX, we had this situation where our RX L-core cache was being depleted, so it had to go to the packet mbuff pool. And the TX was exceeding its threshold, and so it had to be flushed out to the packet mbuff pool. So we can end up with a situation where we're defeating the cache, right? So, we have some control. I mean, we could look down into the situation. If we know how things are going in the system, we might actually be able to, at the application level, do allocations and freeze, go over to the TX, wherever the TX is running, we might do an allocation over there and then send that back over to the RXL core. But it's hard to do this from the application level. So, maybe if we had some APIs to monitor and manipulate this. Yeah.
We see this particular thing. The pipeline we build has almost exactly the same syndrome.
Yep.
Right. There's actually a reasonably simple fix to it.
Oh.
So if you look at the underside of it, it's a ring. The underside of the cache is a ring.
Mm-hmm.
The underside of the cache needs to be a stack. If it's a stack, it will change it around. So instead of a ring, go after a stack at the bottom end. This is something we can do. The other side of it is, even though we don't actually change it, the TX doesn't really have any sort of bearing on the cache anyway. It's going to get flushed at some point. It's just a bulk flush. Reduce the cache size. Right now we don't allow that as a start sort of API, but the cache size is a per L-core parameter.
Yes.
We just don't allow it as being modifiable L-core. So we could put an API, you could reduce the size of the TX cache, which essentially means if you imply a stack underneath, you could keep more hot stuff in cache.
Mm-hmm.
The LLC. So we could make those changes. Do you have an idea how much it would actually benefit you?
Not yet. We don't.
So a simple example: if you run two things in the same L core versus two different L cores, and just for a small packet pipe like this, do you see a large performance variation because of this?
Well, we have a couple of applications where we did.
You did, right?
And one of the issues we had was where we could actually free a packet MBUF on a core that would never do an RX or a TX.
Right.
And so then they just stay there forever, right? Until maybe at some point you fill up that cache. So another thing was, how, on that core, I don't want a cache. How do I just say no?
Correct.
Right?
But the parameter is there, we just don't expose it.
Okay. Well, we went in and fixed it.
Okay.
Just under the covers to see if it, if we could prevent it from happening, and we
Right.
could.
Okay.
That was just leaking away packet MBUFs until you filled that cache up.
Yes. And it's pretty large because...
Yeah.
Interesting.
Did you see, okay, you stopped leaking MBUFs, but did you see a performance impact due to not having the cache? Because that's, to my mind, one of the main reasons we have the cache is to stop hitting that shared resource for that ring. So, if you've got RX allocations on one core, freeze happening on a different core, you're going to have this core-to-core cache line move, passing the data pointers across, whether it's a stack or a ring. So you want your caches there so that you only do it again per 32, per 64, 256 packets. So I wonder, did you see any performance hit? Was your free of your MBUF running a lot slower, not going through this cache? Because every time you free the packet, you were actually doing a multi-producer put with a big, compare and swap operation in the middle of it.
Yeah, our application at the moment right now, we run on one, when we run this code in the VM, we run it on a single core for the most part.
Okay, because as I see, as with all core-to-core problems, you actually have 2 or 3 problems underneath it.
Yeah.
So there's one problem is getting the pointer to the buffer across, which is where the MBUF caches come in and the ring comes in. And then you got your second problem of the actual buffer data itself and where it's cached. And as Venki was talking about it with the ring, with a ring structure rather than a cache, a stack, whatever the buffer's freed, by the time it gets to the other end of the ring to be reallocated again, it's actually dropped out of your CPU cache.
Right.
So I'm wondering which problem is actually worse in your case. Is it really a problem getting the pointers, or is it actually a problem of your data buffers themselves?
Yeah, and we need to do more analysis there. It was like a week ago that we started thinking about, well, what is this problem, right? So the observation we made was about a week ago, but we were just starting to look at how, where the real issue is, what's the root of it, and how many are there.
So interestingly enough, right, there are 2 other applications that have exactly this problem. One's the pipeline. This pipeline tends to go core to core to core.
Yeah.
Has exactly the same issue. The second one is OVS. OVS tends to do exactly the same thing. It has allocates on one core, and then the eventual free might happen somewhere else.
Right.
Right. So we do see that same particular syndrome. So I think we should look at trying to fix it in some shape or fashion pretty quickly.
We had the same problem.
So I think this is something that we should look at.
Well, we've started discussing it
Yep.
before.
So we've discussed it for a while now, right? We know there are applications that
We
have
haven't
this
found the
particular
silver
thing.
bullet yet.
Yeah. I think there are 2 or 3 things we could do. So the biggest problem you see is on a ring, you attach enough elements to the ring, let's say 8K, at some point they're going to fall out of cache, which means the MBUF becomes a memory read. And you can actually measure the number of memory reads that happens. So maybe that's one thing we should look at, is that actually causing a limiter? Because that we could see. You could actually see memory reads come back. The second one would be the actual sizes of the caches themselves, and that's another interesting thing. The ultimate story is, how can we get this footprint of the memory side down enough between changing cache sizes, changing stacks, etc., so that you stay within a smaller memory footprint.
Right.
I think, Steve, this is something that we've talked about in the past as well, right? Yep. Similar problems.
Okay.
Yeah, so Venki, do you think Broadwell DE can help with that, where you have a lot better control over memory and cache?
Yes.
Yeah. So send me the results when you get them. Well, no, Venki knows the framework we're using, so pipeline is fairly close to that.
Yeah. Okay, good. Related to this was, when we first saw the problem, we said, well, maybe we need to just make our packet MBUF pool bigger. Well, that didn't go very well. So, what we noticed was if we did nothing else but double the size of that pool, our performance, went down, right? So, so everybody here already knew that. But, so I don't know if there's, obviously you want to use those local caches if you can, but sometimes you can't avoid it. So, in the event that you have to go retrieve from it for RX, or you have to flush to it on TX, is that acting like a FIFO? Is it least recently used? It seems like if the bigger we make it, we're going to the oldest thing in that pool first, and maybe that's for reasons of avoiding locking, or or ref counts, or I don't know, but
no. So what we did, so if you go back to DPDK 1.2, we had two FIFOs. The cache was a FIFO, the ring was a FIFO. Okay. So what we did in 1.3 was change the cache to a LIFO, but the ring is still a FIFO.
okay.
The intent of it was, the LIFO gives you lock to SALOC, but there's more than lock to SALOC. It gives you hot cache, gives you hot MBUFs that are already likely in L1. But the FIFO gives you control to say, look, if I've got this packet that's essentially a TCP ACK that I'm freeing back, I don't want to see it again because it's likely 5 milliseconds old. So I don't want to reuse that MBUF. That was the reason for the FIFO. So I think we've got different profiles of applications that want different things. So I think what we should do is probably attach different allocators and pick them depending on what your application actually wants.
Right. So we can select it at a NIT time and say we want this pool to behave this way. Okay.
I think that's probably the goal we should go after. If anybody thinks different, speak up. But I think giving that flexibility is probably better for a lot of TCP type or long holding applications that will essentially fall out of cache anyway. And if you put a LIFO in front of a TCP stack and said, hey, the next packet is something that I saw 5 milliseconds ago, that's going to be a problem as well. Okay, so we've seen both sides of the application. It's just not one, unfortunately.
Yes, so thank you. I think that's a theme.
I just want to add one thing to this. So the ref count comes in a way, right? Because the MBUF is old, and then you need to decrease your ref count. So actually, from my point of view, I would love to see an option to get rid of ref counts because that's ruining my cache.
Agreed. No, I think we make it a little more flexible. You attach a different handler for different things. I think that would be more ideal.
Yeah, just an observation. I think a lot of DPDK, there's too much policy embedded in the mechanism, and we've got to try and pull that out, return codes, these type of things, per core allocators. And
that's too little policy. We'd like more streamlined to do certain things in one way and only one way.
That's a good comment with RefCon and the others. There are too many things that become, so the TMBus become too much complex. And we are writing an application on top of that, and in our applications, we are already managing these data. And why do they show up in RTMBus? We don't care. If we need it application, we have fields, we have quite data structures to write it, and we manage it. But please don't keep adding more
knobs.
Yeah.
More knobs.
So we went away from this in the past, right? So what about two different MBUF structures? One 64-byte minimal, one more, more application driven, more complicated. Would that be something that we would consider? Why? See? So again, remember, different applications deal with different things in different ways. Some applications like more complicated, more beefier structures, some don't. Yeah. The routing application honestly doesn't care.
Yeah, but in the application, we take care of, let's say, the extended needs of the
Some do, some don't.
So, if I could jump in here. So it sounds like what you're saying is that it really isn't even applications, it's the type of traffic that could change. So even if the application is OVS, in one hand, if we're handling big packets, we need to tune it a different way in majority. On the other hand, if we're handling small packets, we need to tune it. So some of the optimization for small packets is actually decreasing our potential performer for large packets because of this cache problem.
So, perfect case in point, right? For something like TSO, we need to carry. For TSO, we need to carry more data. If you want to have something that does TSO, it's going to be more data. You do it in the application, right? You do it in 6.8. But OVS for VertIO will need to carry it through the MBUF. So you have two different profiles of stuff. So I think at some point we did this, we went away from it, and we actually took packet MBUF, control MBUF, and broke it back to one common structure. Maybe just go back to an overloaded structure and essentially a version 1, version 2 MBUF, and you use one of those two. That's an interesting way of looking at it. Or find an extensible way of looking at it. We've got to find something that will service both sides.
Yeah, I mean, I think it's a trade-off between, the KISS principle, right? Keep it simple, and having the flexibility to do what you need to do, right? So different applications need different behaviors. So I don't think we'll answer that question today, but that's going to be an ongoing discussion. I think there are going to be trade-offs every step of the way.
No, it is something to think about. I think think about it as a community as to what we want.
Yeah. We just want it to go faster. So I'm sure everybody probably already knows this too, but it was a discovery process for us. So one of the things that we learned, initially we started off with IGB, and then we went to IXGBE, and then IXGB-EVF as we were allowed to. And one of the things we discovered was, well, all PMDs are not created equal. They don't all implement all of the APIs. And we got alarmed at first when we discovered this, because we happened to be using an API. That API wasn't implemented across all of the POMO drivers. So when we first tried, I think it was VMX Net3 or IXGB-EVF, and we were calling RxQ count.
I have implementation of that for both those drivers related to the
Yeah, so the implementation would be awesome to have that. But the one point is the fact that there's a hole there where if the protection mechanism wasn't implemented, you can just fall off the face of the earth. Yeah.
This information is very useful, I think, for everyone. Would you consider to contribute this kind of table in the documentation?
Sure.
Thank you.
The only drawback to it is it's a static thing, so I looked at it, I think that's from DPDK 1.8 when I went through that. So that's the only, it would be nice actually to have a way to generate this table automatically so that, we could go through and it's not hard, it just takes time. Right?
Does it mean that for new drivers evolution on the DPDK we should enforce a minimum, and if it's not there, then we keep asking to the driver provider?
I think that's one thing. Yeah, I think that's one thing. Another thing we could do is a different mechanism of handling the problem. So today it's you opt in to detecting that there's a null pointer in that vector table, right? If the DPDK infrastructure, if the RTE API actually goes and checks that there's a null pointer there and it may then return an error, why not take the table when the POMO driver registers, it gives you the table of function vectors, walk through it. If there are any null entries in that table, put a stub in there. So that means you got to have a stub for every API, but then if somebody happens to call that, they're going to get some sort of error from the stub that says,
Well, the downside of that, they're function tables, and all function tables need to be immutable for security reasons. Because if somebody can have a group it, find a buffer overrunning your application, and they can get a hold of a function table.
right.
Actually, so Steve, you could do this without
Yeah,
having that particular problem, right?
Yeah.
No, but I think that's a good suggestion. I think we need to figure some way of at least enforcing a minimum.
Well, the other one is, I think the driver register function should you try to register, you don't have to key functions.
Right, so you could do that. I mean,
You want to support it, so you include create another indirection.
Well, but the point is that if there's some sort of ones that we just expect people to do, like you need to have a queue release function because even if you stub it, that's fine, but we're not going to take care of you. When you register the driver, you should just say, no, I'm not going to let you do it.
Yeah, but so Steve, the logical extension there is what we talked about yesterday, live migration, right?
Yeah.
I need a certain set of functions that must be implemented for live migration.
Right.
If it's not there, it's not going to migrate. And by the way, these are some drivers, and it's kind of shocking that that's all Intel drivers, by the way, just FYI, right? Okay, but there's more that have different APIs.
Yeah, yeah.
Right? And even we have that big a variation is kind of.
Well, that, you know, when I first made that chart and I saw all the red in it, I got really worried.
By the way, it also shows you one thing, right? Even within Intel, our focus is that one green line.
Mm-hmm. And we noticed that. So it's an interesting problem.
Yes. But it is one that we have to fix.
Okay.
It's just how do you get everybody to agree on what that minimum subset is? Because everybody's,
Yeah.
you know, what happens if everybody wants a different function in that subset?
Of course, everyone wants something different.
Yeah.
But we've got to at least if you look at the kernel does this today. Okay. There's no reason why it shouldn't be done here too.
Okay. I mean, I think these are things that probably everyone already knows, you know, and it was illustrated by that previous slide that the POMO drivers are all at various levels of maturity. So, you know, if you're coming into the DPDK community, it's important to be aware of that, you know, they're not all the same maturity as the NIC driver or the kernel level driver, and, you know, those that exist in DPDK are not at the same level of maturity. And sometimes it's hard to find out, you know, if I want to use VMXNet3, you know, what's it missing, right? So you got limited visibility into the capabilities of the POMO driver. I don't know that there's a good way to solve that because it's sort of the same problem of what features are baseline, what do you have to have, and do we have APIs to actually determine what that baseline is? So, you know, for example, you know, VMXNet3 today, Stephen has a patch, we tried it, it worked for us, but it doesn't support Jumbo today. So, you know, there's no way to know that other than you've been through the code or you've tried it and it doesn't work.
Well, I think we need a real driver test suite because there's a whole lot of other things too, like ref counts, indirect buffers, chain buffers. What's the maximum change you get? Will you get, you know, a lot of those things we aren't testing for. Maybe Intel has a magic test suite, but
No, but Steve, you bring up an interesting point, right? So the general philosophy we followed is that if you have, you know, specific acceleration in those drivers for specific things, build your own. But it also means that we've got to figure out how to allow the capabilities to be discovered, which we don't have, and some baseline that we actually need to agree on.
Yes. Yes. You know, another thing that we noticed was, and I know I kind of keep picking on the IXGBE driver here, but you know, limited visibility. Some POMO drivers have multiple modes of operation, and some POMO drivers decide on their own what that operation mode is. So, for example, you know, if you build with vector mode on IXGBE, then, you know, the IXGBE POMO driver decides when it's going to turn it on or not, based on what the NIC can do, right? The only way you can know that is if you happen to go look at if you have access to, which may be a problem in a deeply embedded system, to the log output, the printf output of that driver, right? He sent it out to standard out, but who knows where that went in your application. So there needs to be a way, I think, to be able to determine, you know, what mode if it runs in multiple modes, then there's got to be some way to get to that data so that the application can at least detect whether or not it's running in this, you know, in this mode of that.
Sorry, can I just ask, why does the application need to know that? Because certainly with the IXGBE driver, I mean, you've got a set of flags that specify the conditions you're going to run on, whether you need jumbo frame support or not, and we just pick the best mode that meets your constraints.
Because my application runs on anybody's server. I have no idea what they have, and when it comes back with a problem, I need to be able to say, go hit the CLI and tell me what happened.
So Bruce, interestingly enough, simple one, right? Very simple thing. I need to service X million packets per second. So I do 1 core or 2 cores to do it. Depending on the vector driver or non-vector driver, you get essentially 2 different numbers.
Yeah,
right?
But for a given application, it needs, it either needs jumbo frame support or not, or it needs, these various offloads, which is what, it's the support of those offloads that
Correct.
determines whether we use vector
But
driver or
it's
not.
a little more complicated,
And
right?
if you need those offloads, knowing whether or not you're using the vector driver isn't going to make any difference, because if you need the offloads,
No,
you
it
can't
does.
use it.
So when they're trying to satisfy an SLA, it does. Because they need to know how many cores or threads to allocate for whatever functions they're dealing with. And they don't know that because it's the system underneath is indeterminate. So if it's going to deliver you packets in 20 cycles or 40 cycles or 60 cycles, they need to know that part.
But that's not going to vary from application instance to application instance.
It might.
Yes, it will. My
It will.
application incident might run on your box or somebody else's box.
Yeah.
So-
They may have different
But
mix,
if
right?
you're running, if your application uses certain features, okay, it will always run with driver A or driver B.
Absolutely.
Okay, the vector or non-vector. And it doesn't matter what the hardware is, CPU is underneath, if you're using that Niantic NIC with that IXGB driver for your application with your given offloads, it's always going to be either the vector or non-vector path, irrespective of the
In that
CPU
particular-
underneath.
Yes, that's right. But how do I know that if I have a customer that's having a problem and maybe there's a bug in the vector driver? I can't even tell you that he was running the vector driver.
By the way, which there was. Checksum. The checksum flag wasn't being set on the vector driver, and there was a performance inversion in a bunch of places that was a little bit challenging to debug.
Right. It's because I don't own the hardware, right? So I can't, and I need to be able to detect that in order to support that environment.
So in this case, this is where the user may have tuned the offloads that you need.
Well, the user doesn't. The user put a VM on a box that has a NIC in it.
Okay.
By the way, the perfect test case for this is OVS, right? OVS doesn't care two hoots about what driver's bound underneath as long as DPDK NetDev sits there. It expects that DPDK NetDev has negotiated all this stuff correctly.
But what I'm just wondering about is, if you know it's Niantic NIC and you know your application, do you not know which path it's going to take based on that?
We don't know it's a Niantic NIC.
Okay, well that's
In fact, they don't-
different. But
they
that's
don't- they-
different to knowing which.
No, but they don't
direction
care
takes
what
path
NIC
Niantic
is sitting there, to be quite honest.
Yeah.
And by the way, the other side is, there's not one version of Niantic NICs, right? There's 4 of them, there's 5 of them, and there's 4 12, and there's 5 of them, and
But that's a different question though, to whether it's using the RX scattered or the RX path.
no, agreed. But I think it comes down to the same thing about querying what your device is capable of doing, supporting that.
Okay.
And
So
reporting
a
out.
general API that tells you
Yeah.
it's using this RX function, this TX function, sounds like it may be more specifically what you need, because that'll also tell you the driver
Yeah,
as
I
well
think-
as the actual
Yeah.
function within the driver.
Well, but it could be totally PMD specific, right? You can have for one PMD, it could be 2 scatter together functions, like we have for some time for HP, we have one just scatter together and another scatter together plus overall. Okay, it could tell you scatter X is negative, it doesn't
Tell you which it is.
What you would do is it not.
Right.
So it's a thing we've got to look at.
Yeah.
This is part of the standard growing thing.
So, so it sounds like, to summarize, that we can have side effects of really remarkable changes in performance as we migrate a compute node that has Open vSwitch running from one server to another to the cloud, and it's going to behave differently even though they're both running DPDK, even though they both have supported NICs, because some NIC might make a different decision in terms of how it's going to optimize as opposed to the other NIC, and the user, whoever is looking at the packet performance, will see some variation in performance, and it's going to be very difficult to explain why. I don't know what to do about it, but but that sounds like what we're talking about, and this is, you're naming one case with the Niantic, right? But it's going to show up in a number of different cases.
Especially in the encapsulator world, right? So there are certain versions of Niantic that support VXLANs, there are certain that don't. So if you had a VXLAN interpreted story, you should be able to figure out which ones do, which ones don't, without looking at the LFPCI.
Right.
That's what we're actually ultimately trying to get to is, can we, to the upper layers, to the application that uses a VXLAN protocol stack inside, tell them that, hey, look, that's supported, not supported. Today it's a guess. And this, it has an impact across the system eventually.
Yes, I think it comes down to who the application is, because later on I'll talk about controllers. You know, we have other things as a controller. So all this low-level stuff that people are talking about now, it means nothing to a controller where a service provider says, I'm going to deploy this path based on the number of dollars you pay me. So we need a capabilities discovery. You've got to look at where you are in the stack to say what's relevant. So,
correct.
And, I'm sorry just to repeat, but exactly what you said before. When you are on Linux, you use the kernel drivers, you run ETH tool, and you have the answers. You know if the interface does VXM upload, that is payload, does checksum uploads, and everything is gone just because we have cut and pasted the driver to the username. So when you read that documentation, for instance, to answer to your question, Thomas, the documentation tell me here is use ETH tool to have informations. So I heard yesterday that I think it was Bruce, maybe to try to synchronize the KNI and so on. Okay, we are going to add some more complexity in the synchronization mechanisms that may even create sometimes some race conditions for that. Because we keep having this design. So I just keep repeating the same thing, but it's once again another issue because of the way the drivers are. Okay. I just wanted to raise the point. So we can keep fixing on top of that with ETH tool extensions and so on, and we can extend your ETH tool proposal to have this information because you'll have it from ETH tool. So is it the way we should go, or should we try to clean it from the kernel?
Right. I don't know the answer.
I guess it means that everyone doing the need drivers, we need to tell them, and Mr. Intel, Mr. Celsius, please stop.
Yes. No, I understand.
So that's not going to be the way it will work, right? You have to build it, fix this from the ground up. This needs to be fixed inside DPDK. You can't say, I'll rely on the Linux kernel, because the Linux kernel is not what you will run sometimes. We're not a Linux kernel-only system. Let's be quite blunt about that part too.
When I am on BSD, I can have the same API to access the packets. Microsoft are proposing APIs to access the packets. So all the vendors can have the API, and in each operating system there are tools to monitor the network ports.
No, not exactly.
So I mean, we are not going to talk about bare metal DPDK.
It's not only about that, Vincent. There's a lot of operating systems that do things very, very differently. In fact, there are a lot of embedded use cases that don't actually even run Linux or BSD or Windows or something else. There are systems like that. So, I mean, this is not something that we can not avoid. It's something we need to do. Yes.
Do we have two versions of the drivers?
So healthy debate. Healthy debate. I mean, into your time, huh?
No. Okay. It's a good point.
Well, the rest of this slide is pretty much the same sort of thing. So we've actually been through that one all. Another thing, Andy mentioned, embedding policy in DPDK. Here's another example where sometimes the choice is made, down at a very low level that, something's gone wrong. I'm going to exit. I'm going to abort. I'm going to panic. That's not good in a product. In some applications, the application might still function. Maybe I've got other interfaces that aren't under the control of DPDK that I can, or administrative interfaces that some administrator is using to figure out what the heck happened to this box. Why is it not working? But it can't because the application actually went down. So there needs. I think we need to provide a mechanism for the application to set the failure policy. Another thing, and I'm trying to move a little more quickly, is not all drivers, Polmo drivers, for example, report errors. So again, I picked IXGBVF. Sorry about that, Bruce. But one of the things we noticed, we were trying to change the MTU, and for various reasons on the host side, the PF said no, you can't do that. The VF said, okay, I got a knock from the PF, and it said, yep, I did it. Right. So now I've changed the MTU. As far as my application is concerned, the MTU has been changed, but really it hasn't. And in the extreme case where we were running here, we were running ESXi with a V-switch, and the result of it was not that we couldn't get packets of the MTU size that we set, but that we could get no packets in or no packets out. It's not a DPDK problem, but the fact that we didn't even know, we had no way to fix it, right? Now, yeah, we could look at that particular case and we could go back and turn around and read the MTU, and the MTU, maybe, hopefully we'd find out that it didn't actually apply to change. But the reality is, we need that information back up in the application. The other thing that I mentioned earlier about, when we were talking about whether the IXGB was in vector mode or not, well, you can look at the output, the printf output, it'll tell you that. It prints it out if you can get to it. In our particular application, we have a pretty sophisticated logging system. Things from standard out don't go into that logging system because we use a whole different mechanism, right? So
You can redirect RTE log to something else.
yeah, but they don't all use RTE log. RTE log, yes. Printf, maybe we could override
There
printf.
should
But
never be a printf in the DPDK code. No, RTE log goes to a thing which then you go to syslog, or you can make it go to something else if you need to.
yeah, so I think just making sure that everybody's using RTE log, that we can that then we can bind into that. So we'll definitely look to make sure we.
So I thought that was the. I didn't think there were printfs coming out of anywhere underneath. If there are, we should fix them.
There are some. I'd have to go back and look. Maybe it was coming out of some of the sample code.
Sample apps have.
Yeah, sample apps have them.
That's fine.
Yeah.
But the library shouldn't.
Yeah. I'll double check when I get back.
It's an easy fix.
Yeah.
Well, I just look in the ACL code, it has lots of printfs.
There you go. I had a script that was pulling them all out. I thought that it came out in other places besides the sample code, but I couldn't remember for sure. Again, I don't know how many people in the room use DPDK in a 32-bit application. So most people don't, right? So all of you people that don't, remember that there are those of us out here that do. And so it's a challenge actually if you're one of the few people doing 32-bit stuff. We're the few who test it. Okay, I gotta go. So you can look at the slides later. Yeah, Andy doesn't want to talk. Dynamic linking is assumed. One of the things I noticed or we hit was when the Polmo driver registration was moved into constructors. Things suddenly didn't work. I had no Polmo driver. I had no NICs anymore. Where did they all go? Well, you need to take special care if you're linking static libraries. So for any of you out there that are using them, have you already encountered this? Maybe you have. If not, maybe that'll help you. And again, I mentioned earlier, just supporting legacy tools, kernels, that can be a challenge too. So, things, we'll find, a new header file that's being used that's not available to us. I think one of the problems those of us that are using sort of legacy environments have is how do we handle that in a graceful way? So, if the header file that's being included in some DPDK code and we can't support that in our environment, how do we disable that in a way that's acceptable to the community? We want a conditional compilation all over the place. So what's the best approach? Moving forward, I mentioned earlier, we had for a long time been kind of drinking from the DPDK fire hose. We've found some issues. We've worked pretty closely with Intel and with Larry in particular to get those things pushed back. So a lot of the stuff, any of the fixes, the being able to do multiple threads per L core, some of the NUMA stuff, some other things have all been pushed back up or in the process of being so. But for us as Cisco, we need to start contributing back and standing on our own 2 feet. So that's our goal and our plan. Like the guys from Ericsson here said, we work in a big corporation, right? So there's challenges and things move slowly, but that's what we're working towards. So that we can start committing, contributing directly both feature-wise and bug-wise, bug fix-wise. Thomas?
That's great to hear that you are going to contribute some bug fixes and enhancements, so it will solve some of your issues. But there are some issues about some design rules or make the community aware of some issues. I think you can also fix this kind of problem by submitting some patches for the documentation. If you want to enforce some design or rule, you can publish it in the documentation.
Okay.
And about other issues, like some drivers send the wrong error, it can also be been fixed by making more reviews, actually. And we are looking for reviewers.
Yes.
So you are very welcome.
Yeah, yes, you're right. And we want to applaud your efforts because I watch you on that mailing list, but it's a full-time job just to keep up with you. Just watching the emails fly by. It is. Yeah. One. Okay. So we hope we can help. We hope we can.
We have one vein key as well.
Yeah.
We've got a problem here.
Yeah. So that's all I had. I'm gonna switch over for you, Andy. Let me get out of this presentation. You just hang on just a second. Yeah, let me